Okay, it's working? Okay, perfect. So thank you, everybody, for staying still here. So this is the last session before the closure. So thank you very much. I think we have had a very interesting presentation from Nuno, speaking especially about the vision of the states. And now, as one of the objectives of this big science industry forum in Spain is to give you a general overview of the opportunities and the picture of how everything is going in the different sectors in the big science. I think I agree that we are in the most exciting moment regarding fusion. So that's why we have here a selected group of European startups. Okay, so in order to have a general overview for you about what is happening in Europe and what opportunities do we have. So, okay, we will start. This session will have two different parts. The first one will be short presentations of each of the startups, showing their advance and their collaboration opportunities. And then later we will have a discussion between all of us. Okay, so we could start with you, Esther. Yep. So Esther Cantor is from Proxima Fusion.
Yes, thank you. We seem to... So hello, everyone, and thank you for staying with us this second day. My name is Esther Cantor. I'm coming from Proxima Fusion. And Proxima Fusion is a Munich-based energy company. We have been founded 2 years ago. We are based in Munich, but we have two other locations in Europe. One is in Switzerland near Zurich, and another one in Colham near Oxford in the UK. So in the last 2 years, we've grown from about 10 people to over 100, and we have received over 200 million euros financing, mainly from private investors. We do receive grants and subsidies also from the government in Germany, as well as from the EU, but the majority of our investment comes from private companies. We also have a peer-reviewed publication, which you can find on our accelerator concept, which we published last year. So if you're interested, it would be great if you could have a look at that. You can see our team actually pose on the picture, and the picture was taken earlier this year at Greifswald, which houses a W7X, which is a research accelerator machine. Our network here on the map, you can see, is quite wide-ranging: industry partners, research partners. I have my colleague here today with me from the procurement team, and we would love to get to know more Spanish supply chain players. As you can see in this map, it's so far Fusion for Energy, but I do believe that this day we have made quite a few new contacts and partners, so we would love to extend that network with more Spanish companies as well. And here we have our co-founders and two MIT graduates and almost everyone from experience in the accelerator field. So it is great to be led by a team of nuclear physicists and engineers. They really define the environment at the team, and it is a really special place to work at. And this is the facility where everything began in Greifswald in Germany. And this is basically where the founders set the stage for the company itself. And you have heard the professor earlier to speak about the case for fusion. So I don't know if this audience needs a lot of convincing. I think one of the things, of course, that it's a safe energy. We are not competing with renewable technologies. We are competing with fossil fuels. Interestingly, I think what is also worth noting is in terms of the development timeline, commercial fusion shares very much the same development timeline that fission does with the AMRs and SMRs. So that is going to be very interesting to see how it plays out. But it does have a lot of promise, and apart from the decarbonization and the human ambition, that also the data centers and AI, and you've heard all about this already. So there's also something that is very peculiar to Europe now, is that energy sovereignty. And I think that is very important, and that is where the supply chain can also play a huge part, keeping the supply chain European and not making us dependent on any other foreign resources, as that was the case for Europe for so long, it will be key for fusion energy success. And I think that should be also very important for the policymakers and something that they look forward to when they select the next big thing to finance and to support. And then just look out to where we are in terms of global competition. And we see the United States, we see China, both Spark and BEST will be apparently turned on in about 2 years' time, 2027-ish. We don't really have a precise timeline regarding the Chinese facility. This is our best estimate, maybe sooner, so who knows. And then for ourselves at Proxima Fusion, our demonstrator facility is targeted at 2031. And the full-scale power plant is in the first of a kind, I might say, in the mid-2030s. So that is the timeline, and you may see that this is a little bit behind the Americans and the Chinese, but it's also a little bit different technology with the stellarator. As you have heard before, it is a magnetic confinement fusion device, but it's a twisted-shaped donut, so it's a bit more difficult to design, but perhaps easier to operate. And here are our timelines, and a lot of the things that we work on actually is determined by these milestones that we set for ourselves. For now, we have been able to keep this timeline, and hopefully we'll manage to do that. I think in a large part, what determines the next phase is, of course, the ability to access those resources, those capacities, the knowledge, and the contractors, whether they are providing us with services or materials here in Europe at a condition that is suitable also for a startup. Because, of course, startups work in a different way than a university or a research center. More adaptability, more flexibility may be required. And, of course, we also negotiate on price. And this is something to look at when you compare the tokamak facilities and the stellarators. You have heard it in the previous presentation, very well defined. And I don't know if we can start this. Can we start the video? No? Okay. So this was, so just in case, we have fabulous videos online on what the stellarator will look like. And it will most likely be built in, of course, Germany, in our home state of Bavaria. If you have a choice, have a look at our YouTube pages, and thank you so much for your attention.
Thank you very much, Esther. Now it's time for you, Mario, from Kyoto Fusionary.
Well, hello everyone. I will quickly introduce myself and the company, basically. The name of the company is Kyoto Fusionary, and we have a strong vision for fusion industry collaboration that you will now understand why. So that's me. I'm from Malaga. I'm an industrial and nuclear engineer. My main role in my company is about fusion materials and manufacturing. I also do neutronics, some coding, right? And lately I've been heavily involved in business development and networking. I did my first steps in my professional career at IDOM in Barcelona, and now I'm fully committed with Kyoto Fusionary, based at Culham, so the campus of UKEA in the UK. So Kyoto Fusionary is a spin-out from Kyoto University in 2019. We have more than 160 members. We've raised more than $110 million. And we have offices in 5 countries, right? So our headquarters are in Tokyo and Kyoto. We have offices in Karlsruhe in Germany, in Culham in the UK, Canada and the US. So what we do, right? So as a fusion startup, our approach is a bit different with respect to our colleagues. And instead of focusing on a reactor model or a specific plasma physics concept, we are focusing on the technologies that surround, let's say, the plasma chamber or the reactor that would enable a fusion reactor to be commercial. What does it mean? It means to be able to extract energy out of it so that, in an efficient way, so that it can be sold and it can enter the energy grid. For that, we are focusing on three main areas, let's say. The first one is the thermal cycle and fusion blanket cycle, which focuses on the extraction of heat from the reactor. So Kyoto Fissionery is developing technologies and components for the thermal cycle. Connected to it is the fuel cycle, which focuses on the recirculation and purification of tritium that is generated on the breathing blankets. And we also develop components and technologies for it. And finally, our flagship product, right, which are the gyrotrons used to heat up the plasma through microwaves. So this is a summary. Our first, as I said, flagship product are the gyrotrons, which are already sold to the UKA and in Japan, to the US, to heat up different plasma concepts. And then for the fuel and thermal cycle technologies, we are building two main facilities. The first one is Unity 1, second picture here, in Japan, in Kyoto, which will be the first demonstrator of a fusion-grade, let's say, liquid metal loop to test technology. It features a 500 degrees lead lithium loop where we can test our, as I said, our new components for the commercial reactors. The most interesting part now is for Unity 2, which is focused on the fuel cycle, we have engaged in a very important public-private partnerships, which is via the creation of Fusion Fuel Cycle Company. It's a joint venture together with the Canadian National Laboratory. And finally, recently this year, Kyoto Fissionery is also leading a public-private consortium for the design and build of FAST. FAST is the Japan's, let's say, new proposed reactor. It's the equivalent to a STEP in the UK, but with a different focus, not so much focus on producing electricity or having achieving a nice TBR ratio, but just for the integration of technologies. Apart from these main facilities, we also collaborate with other industries to adapt components to fusion conditions, such as, for example, pumps to tritium-compatible condition, to high magnetic field condition. We also provide design engineering services, multiphysics simulation, neutronics, a focus on fusion, and mainly on the fuel cycle, we are developing getter beds, palladium diffuser for the separation of isotopes, etc. So Kyoto Fissionery is mainly doing components that might be useful or might be needed by any other fusion actor developing a reactor if they seek to sell their energy or they seek to sell the electricity to the grid to make it efficient, right? Public-private partnerships is the core of this session, and it's already been introduced by Eric and by Nuno in the previous talk. And it's already been, let's say, followed by several countries. So to begin with, the European Commission, for their guidelines on the future of the European competitiveness, as you can see here on the screen, Mario Draghi already mentioned that fusion energy will only be achieved or deployed through the creation of PPPs, public-private partnerships. Public-private partnerships, what does it mean? It's very simple. It's a relationship between public and private that goes beyond client-supplier. In simple terms, it means that public, the government, share the investment risk together with the private. So they engage together in a very high risk, in this case, fusion project. So Kyoto Fissionery is now leading two main PPPs. The first one, as I said, in Canada, fusion fuel cycles, and the second one in Japan we create another company, which is called Starlight Engine, which will, together with the Japanese government and laboratories, design and deliver the first Japanese demonstration reactor. And I have included here on the right side of the slide some other examples of PPPs that, as I said, do not rely on the standard client-supplier approach. For example, the UK is doing things, is providing quite a lot of examples for this topic. One of them is, of course, the procurement of a step. The UKEA, well, the UK government created another actor above the UKEA, which is the UK IFS, which is basically a company focused on just delivering and designing a step reactor. It's not restricted by the very public regulation, so it can operate more freely and more quickly. And another one I would like to highlight before finishing is the milestone programs from the US, which was also used for the transition between the shuttle for the space travels to the now private space travels. And it was the commercialization that have pushed, in this case, the technologies way quicker than when they were solely restricted on public work. Together, and hopefully that PPPs will work, and we need to be creative in how do we design them, commercial fusion will actually be achieved. It's just a matter of time. And for those who love sci-fi, as myself, fusion comes before going to other planets, exploring the galaxy, etc., right? So humanity will go through fusion at some point. So thank you very much.
Thank you very much, Mario. Now it's time for Florian Wasser from Focus Energy.
Well, good afternoon, everyone. My name is Florian Wasser. I'm a physics professor at the University of Applied Sciences in Bingen, which is close to Frankfurt in Germany. And I'm a senior scientist at Focus Energy, and I'm very happy to represent the company Focus Energy here. And as I just learned, I'm not only representing the company, but also our concept of fusion, namely inertial confinement fusion with lasers. And with this, I would like to start with the very big success of the National Ignition Facility. After many years of research, the National Ignition Facility in the United States finally made it and demonstrated that fusion works, that the concept of inertial confinement fusion works. And this was in 2021. And this was not a single event. They could repeat that and even improve it. Finally, they achieved a gain, which is the energy output compared to the laser energy input of 4. So they got 4 times more energy out than in, which is really a great success. And remarkably here, our company Focus Energy was founded almost at the same time of this initial event where NIF made it to demonstrate that fusion works. But we are not there yet. We have not yet achieved the goal. So with the NIF ignition, they achieved a gain of 4 in a single shot event. And where we want to go is we want to have a commercial fusion power plant, which means we have to increase the gain to roughly a factor or to roughly a gain of 100. And we need to achieve that with a repetition rate of roughly 10 hertz. The NIF event was, even though they could repeat it, still a single shot event, so a single experiment where they could achieve that. So a lot of work has to be done to achieve that. And some people usually compare that to an example in aviation. So the NIF success was or is compared to the first demonstration of the Wright brothers that mankind can fly, and where we want to go is the commercial airplane. Focused Energy is taking that challenge. We were founded in July 2021 with the goal to commercialize fusion energy. We are an American-German company with 2 headquarters, one in Darmstadt in Germany, where I'm based, and the other one in the US in the San Francisco Bay Area. At this point, we have about 70 employees, plus contractors, plus many, many collaborators, and the company is growing very, very fast. Our approach, unfortunately, I don't have too much time to go into all the details here, but very briefly, our approach shares a lot with the approach of the National Ignition Facility. So our target is heated, it's compressed, and at some point where the compression and the heating achieve the right conditions, we achieve ignition and finally burn and energy production. I said it shares most of the stuff with the National Ignition Facility, but one thing is different here, which is we are using laser direct drive, so the laser is directly used to heat and compress the target, while at the National Ignition Facility the target was put into a whole room and the laser heated the whole room, and the target was indirectly heated by this whole room radiation. The big point here is that laser direct drive is about 5 times more efficient, which is very important and makes it very attractive for inertial fusion energy and for our goal to achieve a gain of 100 instead of just 4. That said, this still comes with several risks and several challenges that we have to take and that we are taking. Our primary capabilities and activities at Focused Energy are science, laser, and target. So we have a very big science department where we are taking these science risks. We are doing many experiments, we are doing many simulations for risk mitigation, and we are working on this improvement or increasement of the gain up to a factor of 100. The laser, here we are working on the repetition rate of the laser systems, of increased efficiencies, and the temporal or the bandwidth of the laser, the spectral bandwidth of the laser is one of the key points where we need development. And finally, the target is one of our core topics where we focus on mass production of these targets and also the injection of the targets into the target chamber. The tracking of the targets is a big challenge, a big task here. Our path to achieve commercial fusion energy is shown here. So we are starting with laboratories, with the laboratory level, so a laser facility and a targetry R&D lab, where we are tackling all these topics I just mentioned. We already have part of that, so that's where we are today. The next step is to put the pieces together in an integrated system. We call it integrated test facility, with the goal to have this in 2029. And the next step then is to put that into a pilot plant. So the integrated test facility is not producing power yet. It's really to test the system. And then we would put it into a pilot plant that really demonstrates energy production from fusion. The goal is to have this in about 2035. Where do we want to do that? We found that there can be many synergies if we use an existing fission power plant, so a standard nuclear power plant, and turn that into a fusion power plant. And what we got here is the fission power plant in Biblis, which was operated by the company RWE. And our perspective is that we establish a fusion campus at this location, at this site, and that we also include our integrated test facility and the fusion pilot plant into that system. There has been a study, an extensive study called From Fission to Fusion, which showed that there can really be many synergies if we do that at this location. There has also been a foundation of a consortium around that fission power plant with many companies. Among those, us, RWE, local laser companies, but also public institutions like the University of Darmstadt, who decided to work together on this common goal to do fusion and to do a fusion pilot plant at this base here. Yeah, and with that, my main conclusion here is that collaboration between multidisciplinary partners from industry, but also from research institutes, is really a key to our success. Thanks a lot.
Thank you very much, Florian. Now it's time for Frédéric Baudry from Gauss Fusion.
Good afternoon. I'm too fast. I will start to speak. Okay, I'm Frédéric Baudry. I'm CTO of Gauss Fusion after a long career at CERN, where I participate actively to build LHC. And I think I know what it is to build a large device and to spend in a clever way 5 billion and what it is to establish a supply chain. What I want to say is that Gauss Fusion is a company who was created in 2023. It's initially 2 persons, now we have 40, and if we are looking with our shareholder around 100 persons. Then we are select, obviously, magnetic confinement, and as our colleagues, we are 3 companies with Stellarator, because we are convinced that Stellarator will be the commercial machine for magnetic confinement. It's a DC machine. Tokamak is a fantastic research machine, but it is a pulse machine, and you have to recharge your central solenoid time to time. And I'm convinced also that with a superconducting magnet would be more difficult with this size. Okay, we are focusing at the beginning, from the beginning of the key technology to reach fusion, so knowing that magnets, we are going to magnets, material, is not new, tritium, and to have the tritium loop, and in the fuel cycle. Obviously, we don't want to reinvent the wheel, and I think it was shown also by my other colleagues. We are establishing collaboration with research institute to work. And what we said that we want, obviously, as a private company, work with PPP, but create our own IP and on the key technology. And we consider us as a company, as an industrial company, where we have many industrial people and to build this fusion power plant. Then this, you can see on the, I don't know what it is on your left, on the left of the things, our founders. The founders are successful company. I will take from the top AEG. It is an Italian company building superconducting magnet, built W7X magnets, built the TF coil for ITER, built some lot of magnet in high energy physics, especially also at CERN. We have the group Alstom Alcimex, where we a large group in France working in fission, defense, and also at ITER. Bruker, very large group working world leader MRI, NMR, and producing superconductors, mainly niobium titanium and niobium-13. Part of niobium-13 of ITER was coming from Bruker, as also now for the new magnets we have in LHC at CERN. Very known in Spain, IDOM. Mario understood you are coming from IDOM, a large company, engineering company with more than 5,000 engineers. And finally, research instrument also in Germany, very well known in terms of superconducting RF cavities, and working also of ITER. For example, they did the helium pump, superconducting helium pump of ITER. Okay, and in another way, we have, as I said, partnership. You can see the list with CERN, NEA, IPP, KIT, and so on, all these institutions working either in energy physics with superconducting magnets or in fusion. What we are looking is not only the design of a stellarator, on which I will come back, but to define a complete fusion power plant. We want to do, and in the global fusion power plant, obviously you have standard part, you have on any power plant, but also to develop in a global optimization what it is needed to have a stellarator, so to say, the power supplies, the cryogenics plant, and all around the tritium plant and hot cell. Our stellarator, we designed, and we took that in terms of, we designed the global thing saying that we want to have the cross-section of stellarator should not be bigger than ITER. We take ITER as a bigger thing, in spite, in terms of energy, 6 times more than ITER, 500 watt. We are designing for 3 gigawatts thermal, 1 gigawatt electrical. We don't want to go to small things because we want to have something we can repair, operate, and to have the things. And we set our field on the plasma at 6 Tesla, and we have the magnet at 11 Tesla. We don't want to have to constrain all, but to be a global operation, global optimization. For that, with the 6 Tesla, we can use LTS and HTS, then we can do that. We have convinced HTS will be the future, but the supply chain is not established. I hope maybe some will do, but also all the problem of quench detection and quench protection and performance, especially under radiation, is not proven. There is no magnet, HTS magnet in operation in the world in any things, in energy physics, in fusion and so on. Only thing we have is a small insert in MRI. Then I think we have monitoring the two, and we will take some decision in 2030, 31, according where are we with the performance and the supply chain for HTS. This is our roadmap. We call fusion with integrity. We don't want to promise we will do the complete fusion power plant in 5 or 10 years. We have a roadmap over 20 years. We have a first phase we're just finishing now in 3 years, 23 to 25, with a CDR. I will come back to that. And now we are starting the phase of engineering to de-risk and to take all the technology we want to use, especially to build model coils. But model coil has a given thing because it will be half of the final coils, and to produce, to cool down, to test at full current, quenching, and to do that. And we want to have 3 model coils, 2 with HTS and 1 in LTS, and to power the 3 in parallel. To do tritium, to look at tritium loop and all what it is around tritium in the fuel cycle, because we are convinced, and I think we are all convinced, is the issue, the concern of fusion. We have to do that. But we are also looking materials and all the things around fusion. And after that, after this 7 years of engineering, we will go to construction and commissioning, with the commissioning in phase. It's not original, but phase with first plasma with HH, DD, and after that to go in open loop DT and in closed loop, DT in closed loop with tritium breeding blanket installed. To have an operation late, between close to 2045. Okay, this we just issued, maybe you saw our press release, our conceptual design report. It is a document of above 1,200 pages describing all the things, not in terms only about simulation of plasma and so on, but all what we want to build the things, all the material and the supply chain, because we are very concerned about the supply chain if you want to build a so large apparatus. You saw that I just put on things, the things in the Spanish press. I think it was a very well coverage of this issue of our CDR that we give to the Chancellery in Germany. It was mentioned this 2 billion from Germany is important, and we were happy to deliver to the Merch Chancellor our CDR. Okay, then I think this to say about supply chain. I think we are looking each part. For example, we on Gyrotron, it was mentioned by Kyoto Fusion, to be at 6 Tesla, we can benefit all the development made at ITER and also at W7X to stay at 170 gigahertz. We are looking at our production. We are looking at vacuum vessel, large structure. I don't want to go all the things, but we are really looking, I think this is very key things if we want to build something, to look at the supply chain and to develop with company. I think Spanish company could be in the game, all the things to be able to build something in 7 to 8 years. We did also mapping of the first generation FPP. We look at, with the Technical University of Munich, all the criteria in terms of electricity, cooling, seismic condition close to the industrial site and transport. And we found all the sites, more than 900 sites possible in Europe. And I can show you for potential sites also in Spain with 17 clusters and 116 sites. And now we are in the phase to select our site. We want to have the site selected by end of 2027, and we have discussion with the national, local authority and company. As is mentioned, if you can find a former site, coal plant or a nuclear plant, it will be the best. Okay, this to finish is our roadmap. First, the next years about this what we call engineering phase. Obviously, main things, I'll take some example, I cannot do all. We are starting the manufacturing of the 3D coils. We will test our breathing blanket. We want to be a modular to adapt to this fuzzy shape of the stellarator. We will have all the things, and all the tests of vacuum vessel about heating, plasma heating with zero-tone global optimization, and obviously remote handling, because this is mandatory to have that for the things, to be ready for operate a fusion power plant, and to be ready for construction in 2033. I think we are all convinced the time is now to do a fusion, and we are working for that. Thank you very much.
Thank you very much, Frederick. Now it's time for Francesco Volke from Renaissance Fusion.
Buenas tardes a todas y a todos. Bueno, so I'm the founder and the CTO of Renaissance Fusion. We have a two-pronged strategy with a long-term objective of delivering a stellarator power plant, and on the way to that, monetizing deep tech technology in HTS and liquid metals. So we often talk about the scientific and engineering feasibility of fusion. We need to talk, of course, about economics and about being profitable as well. And the profitable realization on Earth of the energy of the stars requires shapes that are not found on stars, because we cannot rely on the gravitational pull of humongous spheres. And we are trying to do it on Earth, so we need materials not found on Earth before. After all, we are building a small star, right? And so we're coping with extreme heat and neutron fluxes. And we identify these shapes in not in fancy donuts, but in piecewise cylindrical donuts, simpler, more economical to construct. And the advanced materials to generate the strong fields in wide HTS, not in any high-temperature superconductor, and to cope with the huge heat loads and neutron loads, plasma-facing liquid metals sufficiently thick to stop the neutrons and sufficiently fast-flowing to extract the heat. So we are Renaissance Fusion. We are a company founded in 2020 during COVID. That really started operation in 2021, raised 60 million throughout its history, counts now over 100 employees from 24 countries in 3 locations, 2 in France, 1 in Italy, over 4,400 square meters of facilities with 11 patent families that you can find on our website. What makes us unique is the ownership of the supply chain of some key components like the HTS, the neutral shielding material, the tritium extraction, from which we have a very promising patent and modeling, the heat extraction as a serendipitous byproduct of the tritium extraction, also a technology for lithium enrichment. And you always hear the acronym SMR for small modular reactors. We do small modular fusion, SMF, if you want, where the small is ultra small, thanks to liquid metal walls allowing to miniaturize your device and distribute and collect your heat on smaller surfaces, and modular, thanks to our wide engraved HTS. We aim at reducing the total cost of ownership and at mass producing sub-assemblies in some gigafactories that can be shipped to the power plant assembly site, assembled together quickly, like solar, which has a major advantage in terms of cost of money of the power plant. So think of solar rather than mega projects like in conventional nuclear, for example. This small modular fusion makes us smaller than Wendestein 7X in producing power from significantly larger power plant designs from competitors. I think it's important to get a sense of scale, get a sense of the major radius of the plasma, the importance of going to aspect ratios comparable or at least approaching the aspect ratio of tokamaks. Otherwise, there's no way we are going to be cost competitive with a fusion power plant. We need to go in the 2 billion ballpark. So we believe in deuterium-tritium stellarators. We feel they only suffer from 3 caveats, and we tackle them. We solve these 3 problems, one being their size and cost. And so, as I said, we adopt HTS or a peculiar approach to HTS to reduce size, with the cost advantages that you see at the bottom, in the size of the reactor and faster HTS production. Basically, we deposit HTS on wider surfaces, 80 times wider than usual, which makes us 80 times faster in production. We stop the neutrons, minimize damage to the reactor via sufficiently thick liquid metal layers, which also contribute, as I said, to making the reactor smaller, to make maintenance less frequent, which is another major advantage. If you do maintenance every 50 years, the lifetime of the reactor, instead of every 6 months, that's a factor of 100, and it's a factor of 200 in cost saving if you include the cost of opportunity. And we simplify the stellarator and at the same time reduce the aspect ratio. So that's done by replacing the traditional way of making HTS tokamaks or stellarators, which consists in buying large amounts of tape, combining them in cables, wrapping these cables in non-planar shapes with millimetric precision, and carefully positioning such coils around the device. So all of this is reminiscent of three-dimensional sculptures. We instead do something reminiscent of aquaforte or engraving, or if you prefer, laser painting with a laser brush on an HTS canvas. So we deposit HTS on large surfaces. Eventually, they will be cylinders. In the short term, they are white tapes. The product, when sufficiently cooled, superconducts in any direction, but by laser engraving, we make it, we force the current pattern, so we impose certain patterns to the current that generate the desired magnetic field with sufficient precision, but yet much more elegantly and cost-effectively. It is, in our opinion, the same change of paradigm as going from individually soldered transistors to photolithographically printed integrated circuits. So we like to picture a power plant as 3 concentric circles. We focus on the first 2, and we are looking for partnership in the third. So our core business is in building these modular stellarators. So it's in the first circle. We also have inventions related, for instance, to gyrotrons, to liquid metal loops, as you have seen, diagnostics controls. So we have a partial involvement in the second circle, ancillary systems. But we build partnerships and co-create value in the third circle. We are interested, for instance, in projects of retrofitting of nuclear or fossil power plants. And I will talk about that towards the end, or approach me in the coffee break. I mentioned monetizing midterm technologies on the way to fusion. One of them is HTS, for which the target markets remains fusion, but since already at the end of 2026, we expect to have our prototypes of HTS, or made prototypes of HTS. We intend to sell them right away. Initially to beta users in the academic and national labs markets, But then there are other markets where HTS is already in demand, so cables, electric generators, magnetic levitations of trains, medical imaging, induction heaters, and I could carry on with medical imaging, with energy storage, for instance. So we are on track to sell these components to these markets, and similarly, the liquid metal that we use to stop the neutrons and extract the heat from our reactors. And to be precise, it's a solution of lithium with lithium hydride with pebbles containing lead. One more time, as fusion as a target market, but as ramifications in other markets. So fission being the most obvious, but there are others, for example, in the space industry. So space re-entry vehicles, the bottom of nozzles of rockets, metallurgy, high temperature chemistry, soft robotics, nanomedicine, you name it. I encourage you to go to YouTube and check our video where you can get a sense of our technology, how it works. You see here some pictures of our team at work. I will be very transparent on the fact that we are fundraising, and with the funding that we are raising, we aim at 3 major milestones, becoming indeed the first producer of wide HTS worldwide, which will automatically give us an advantage in volume of production also for traditional narrow tapes, generate accurate stellarator fields by a tabletop copper stellarator, and putting all pieces together, meaning building the first module of our modular stellarator, so a module comprising the liquid metal layer, the engraved HTS, and generating 10 Tesla stellarator field with sufficient precision. Y ahora vuelvo al español en el momento de cerrar todo, de terminar, para decir que, bueno, por empezar, aquí están mis coordenadas, el sitio web, si me quieren contactar. Como he dicho, ya tenemos una sede, dos en hecho, en Francia y una en Italia, y estamos considerando expandirnos en otros países europeos y de buscar partenariados. Creo mucho en el win-win-win-win, 4 win, entre las empresas pequeñas, las empresas grandes, las universidades y los national labs. Y creo fuertemente en la importancia de identificar un next step device que meta todo de acuerdo, porque todos tenemos cosas de estudiar o demostrar a nivel científico o tecnológico en una máquina, por ejemplo, de 2 metros de radio y de 5 Tesla de campo magnético, orden de magnitud. Y entonces, si ya están en este proceso de considerar esta máquina, por favor que hablen con posibles partners extranjeros. Tratamos de hacer algo para esta economía, para esta sociedad, para este país, para este continente, para este planeta. Gracias.
Muchas gracias, Francesco. Now it's time for our last speaker in this.
Do I need to? It's working. Perfect.
Okay. Thank you very much. Now it's time for our last presentation from Anna Sodatova from Tokamak Energy.
Thank you, Francesco. It was super encouraging. I will continue. When I start this, it's a pleasure to be here today. I'm the last one, but I'm the only one Tokamak and mount this bright company of fusion devices. Okay, so my name is Anna. I'm working as a business development analyst at Tokamak Energy. So our team focuses on shaping company strategy, identifying new business opportunities, and evaluating cost of our future fusion projects. So Tokamak Energy is recognized as one of the world's leading private fusion company. So we've grown a team over 300 super talented specialists working across US, Japan, and Oxfordshire region. So throughout our 16-year journey, We've established a strong track record highlighted by achievements of our main assets as ST40 fusion reactor and our Demo 4 HTS magnet test facility. So from a perspective view, we differentiate our business into core areas. It's fusion technologies and HTS magnets. So one of the drivers behind this structure was the establishment of our spin-off, T-Magnetics. It was last year. And I think many of you noticed that the creation of these science-based spin-offs becomes a prominent industry trend. So by developing T-Magnetics, we are trying to align our company with this market dynamics, and while we try to strengthen commercial potential of our technologies. So one of our main assets is ST40 machine. So it's the world's highest field spherical tokamak, and it's a leader in terms of fusion plasma performance. So currently we are working on advancing this device within the upgrade program. It's co-funded by US Department of Energy and UK Department of Energy, and we believe that this program positions ST40 as a critical milestone on the pathway to commercial fusion reality. So our compact spherical tokamak, ST40, has a major radius just about 40 centimeters. It uses copper coils, and we believe that its scale and flexibility make it as an ideal test bed for novel technologies that power industry will need to test when fusion energy becomes future energy source. So this reactor enables us to rapidly develop, validate, and risk innovations that support commercialization of fusion. But I need to say that ST40 is not one of the other scientific experiments. So we achieved we managed to build a fully integrated fusion infrastructure. So it's alongside the reactor itself, it's a whole ecosystem that includes reactor itself, dedicated control room, and a set of advanced diagnostics. And we have a specialized operational and maintenance team as well. And definitely, we have our digital tokamak flight simulator that we use for training and scenario testing, plasma scenario testing. So, yeah. Here should be the slide about our Demo 4, but I can mention it without any visual aids. So another prominent innovation that we are proud of is Demo 4. Demo 4 is a unique facility. It's 14 toroidal and 2 poloidal HTS coils arranged in a full tokamak configuration. So it allows us to test HTS magnets with harsh condition of fusion environment, and it will provide some valuable insight for fusion design and for the whole entire fusion developers community. Another thing, I think, another thing I have to say, we strongly believe that fusion is too hard for any single entity to solve it alone. So for this reason, we strongly believe in public-private partnerships, and as many of you were talking today, we as a company has as well a global pipeline of PPPs project, and We believe that only the strong network of partners could collaborate in terms of resources, ambitions, and experience to tackle together existing scientific, engineering, and system integration challenges. And so we are involved in PPPs in UK, US, and Japan. Here's the first project that Mario has already mentioned. We are working together in the same consortium. We are part of the milestone-based program funded by US Department of Energy, and we are involved in this project publicly funded in the UK. This is STEP project, pilot fusion plant. And we are working on this LIPS program. As I mentioned before, it's an upgrade program for our existing ST40 reactor. So LIPS program, it's co-funded by US Department of Energy and UK public bodies. So the idea behind, we install gyratron for ST40, we make additional lithium coatings for our inner part of reactor, and so after this upgrades that will take like about a year, we're gonna test our DD plasma with lithium impurities, and we believe it could enhance plasma performance. And so I think it's a great example as well of public-private partnership when we are working together, private entity and public bodies. And it allows us to leverage our main assets and provide very high impact test services. So we believe we can do it more, and we believe in public-private partnerships. So hopefully we'll see more of them in upcoming future. Thank you.
Okay, thank you very much, Anna. Okay, so now we have a general overview of all your projects in your different startups. I think are very, very interesting. You know, fusion history is a history about collaboration. So we have been in the moment we are thanks to this collaboration. But this collaboration has been public collaboration between different public entities, even governments, but also public research organizations. Now, game is changing. We have different actors in the field. We have private entities, but still we need collaboration in order to make fusion a reality. So you know, all we are working together in Europe in order to establish a kind of public-private partnership or some rules about how to collaborate. But I want to know your opinion about how you are facing this collaboration, and how do you think, or which kind of mechanism do you think are more helpful, or which is useful and which is not useful? So we can have a first round, starting probably by Esther, because you have been just speaking a minute ago.
Yes, thank you. So I hate to bring this up again, but Europe doesn't exist in a vacuum. So we exist in a very highly competitive international field, and we see how things progress in other regions. And we also see a global trend of growing from globalization to regionalization, and basically trying to source everything regionally to end dependence on another region. I think it's going to swing back eventually, but for now it is very important for Europe, and not just as individual companies, but together collectively as an industry and as the private sector, to find the right mechanisms in Europe to work with labs and research institutions collectively. We've heard earlier today the Go for Fusion initiative, which is one I think a good way to move forward when it comes to European financing. Alternatively, I think we all mentioned challenges regarding testing and development, so joint test beds and larger facilities are also very much in need. Another thing that is probably could be also useful is working together with the universities on skills development, so providing the next generation of people who would come in, because you see there are 50 plus commercial fusion enterprises in the world, most of them, I guess, in the United States, and there are just not enough people to fill these positions. So there's a lot of, headhunting and going to, other regions and trying to source the best people out there. So I think that is a great also area to explore collectively. But the main thing that I would emphasize is the strength we have collectively as an industry to solve this problem.
Okay, thank you very much, Esther. Mario?
So there's something very interesting. The first historical example of fusion collaboration happened in the 60s, when the UK, the previous UKEA organism, wrongly claimed that they have achieved fusion with the Zeta machine, which is a Zeta pinch concept, and they invited the Soviet scientists to check the results. And because they were also working with the previous tokamak version, and they knew the temperature they had achieved were not enough for fusion. And after checking the results together, they realized fusion was not achieved by the UK at that time, and they together developed a laser diagnostics tool for the measurement of the temperature of the plasma that then led to the success of the tokamaks. But then there were some paradigm shifts, and we are now in, I think, the final paradigm shift of fusion, which is from this boom of private companies to the public-private partnerships. And the idea of collaboration is that, first of all, that in the level of the technical challenge of fusion is such, and the level of investment is that high, that requires to change the scale. And the change the scale meaning countries developing a national view, a national strategy of fusion, then continents. And the first step for any successful collaboration or any PPPs is for the countries to unite all these little laboratories, universities. When I saw all these booths, all these posters today, there are many, many little actors working in Spain for fusion. And fusion might require a strengthened union towards a certain goal. And it's quite motivating because fusion makes us not just to unite the country into one science project, but then to unite countries and private companies where the competence is not that aggressive. Think of humanity as a humanity project. So fusion has the potential to take the species, our species, to the next level of civilization, in which energy might not be a problem anymore. And then we'll see what goes on. That's the thing.
Inspirational. Thank you, Mario. Florian.
Yeah, first of all, I mentioned that we have many scientific challenges that we need to solve, and it's clear that we as a company cannot solve them on our own. And it's also not efficient to do that. There's so much knowledge, there are so many experts out there in the companies, but also mainly in all the institutes. So we need to collaborate with them, we need to work together with them to be able to get where we need to be. And it's not only about the people and the knowledge, it's also about the facilities. So right now we have labs, but we don't yet have the big facilities where we can test everything. So we need to rely on access to facilities in different countries at different locations. And also that we cannot do on our own. We need to work together with the local people. We need to work together with others. And we as Focus Energy are doing that very actively. And for example, I just a couple of weeks ago, I did a big experimental campaign at the Eli Beamlines facility in Prague. And I think we were more than 10 institutes working together doing this experimental campaign. And just because of that, it was a very big success. And besides that, there's also the partnerships and the collaborations with industry. And here, the good thing is that inertial confinement fusion is very modular as a concept. The laser is separated from the reactor, but also the subsystems are very modular. So it's always possible to put several tasks to let the development of a certain subsystem or be done by a certain company, so we can really split the different tasks.
Thank you very much, Florian. Interesting. Frederick?
Yes, it's always difficult to
To
have original. I think it was
yes,
demonstrated today, and I think that we have a tremendous progress made by public in fusion the last 50 years, and you spoke about this slope higher that for the CPU and so on. It's true that now we have big things we have to use. Now there is a new context because some companies are pushing the thing to do that. We have to compare, it was more or less that for fission. We are looking after the Second World War, fission, it was more or less in the same thing. It was initially fission was in the laboratory, in the things, and some private company came and to do that. We have to find a form to collaborate. Definitely, we need finance from things. This was form financing. I fully support you. I think one thing we can start to work is facilities, test facilities. When you have company, I think we mentioned that also, we want to test model, I'm taking model calls, we will not build facility, we have to use facility. Then with facility, we can create this link between private company and institute. And we have not to reinvent the wheel, and we have to find that. A big thing we have in this PPP is IP. Always, this is an elephant in the room when you are setting any collaboration with a private and public. IP is an issue. We have to be clever, agile to mention that. And we have to look at this PPP at different level, at the level national, and I think Europe is, we have to be together. I like that I had a conference with Enrico Letta. Enrico Letta said you have two kinds of country in Europe. You have the small country, you have the countries that don't know they are small. Then I think Europe, we have to be united. If we are not united with, I'm convinced we will succeed to do a fusion power plant if it's a pan-European things. And we have to work together. We have to look at national contribution, European contribution to work. And I appreciate, Alberto, your talks this morning that now the ITER is opening the data, opening the things. This is a very good move, and we are very thanks to that because I think it's helping a lot to have all your knowledge, all the data, book, and so on. This is very important.
Thank you very much, Frederick. Francesco.
Well, I think collaborations should be approached as negotiations. So the secret for a successful negotiation is understanding what the other party really wants and make it clear what you really also want, but likewise what you don't want, you absolutely don't want. So there are some firm points from both sides, and there are some firm objectives from both sides, and then there are some good to have. And those are the things on which we can negotiate and compromise. And in a public-private partnership, if we oversimplify, the public sector probably wants to publish, and the private sector probably wants to patent and build. One trend that I have noticed, also to relate to what Frederick just said, is a tendency to imitate each other. So private companies, they want to publish, and we do want to publish, and we do publish. And public institutions, they want to patent. And sometimes a little bit of mutual education is helpful to put everything in perspective, because I'm afraid that in the public sector, there is a little bit of misunderstanding on how important and helpful IP really is, especially in a sector that will take 10 years or more to mature. And some university groups talk to us with expectations that, patents are super valuable just because one or two pharmaceutical patents from their university were particularly remunerative. But those are white flies, they are exceptions. That's very rarely the case that a patent brings similar amount of wealth to a university. So we might want to readjust the importance of publications and patents. And I also said it's important to clarify what we don't want. So it's important that public collaborators understand that private companies need to be agile and swift, and we cannot afford very lengthy committees to set the agenda, to establish the priorities for the next meeting, which probably we will submit a pre-approval grant, etc. We go to the lab and build. So we need to not only be pan-European, but also, I believe, align between public and private actors on the urgency of fusion and go and build the damn thing.
Thank you, Francisco. Anna.
Yeah, I think a lot of very valuable thoughts. Yeah, I totally agree and support. And I think we have to admit that fusion is not the right place for competition. We are not selling the best, I don't know, oil or gas or any resources. It's quite complex, and I think it's important to keep focusing on win-win situation. As Francesca mentioned, it's important to keep in mind the interests of both sides and trying to find ways to collaborate, not to compete. And I guess quite impressive example was their recent announcement about collaborative roadmap between Eurofusion and China. I think it's kind of thing that we can look at and try to find some potential ways to deliver fusion together.
Thank you very much. And I think it's a good phrase in order to end this round of questions. You don't see it, but we have here a clock which is ticking, so we are really short of time. So I will try to finish with a last round, and I will ask you 3 questions in one. So we will talk about supply chain. So Nuno before told us that it's time in order to define the supply chain leadership of the future or something like that. I totally agree. This is time where the supply chains need to be ready to the challenges we will have in the future. Here you have had the opportunity to meet with many Spanish companies from the supply chain. Luckily, we have a strong supply chain, especially in fusion. My question is about how we are familiar with the tendering process, but in this case, it's different, the approach to you. So it's a very practical question about what is the best way to approach you, and the second part is how do you see the Spanish ecosystem, and the third one is if you want to have a last comment, okay? But it will be in the same, a last comment from your side, okay? We will continue with you, Esther, as the first one.
Yes, so I think as a startup, you will see that we are on all available platforms. So if you may have missed us now with my colleague David sitting over there, you can always find us in various platforms. We are also present in all the communities, so it's not very difficult to reach out to us. We are also as startups, quite communicative regarding our needs. One other thing that I wanted to raise is that the startups collectively, there are fragmentations, but we are most of the times present in the same associations, and we are putting together a joint roadmap. And this joint roadmap is very interesting because it shapes actually the kind of products and services that we will be needing from the supply chain partners in the future. So that can inform you also not just on what is needed, but the scale of what is needed and when is needed. We can work and discuss how can that be made publicly available to you, but definitely I think if you get in touch with us, we can find the right liaisons that you get this information. So that was the who and the what. For us at Proxima, obviously you have seen our timelines. We are focusing on the magnets, so the technologies related to that, the coils, the superconductors, HTS, yes. So those are the suppliers, and then there are, of course, the services that are also very important, the consultancy related to that, that we are also looking for partners on that. We had quite a few meetings. And what was the third question, Eric?
The first question, the second or the third one was if you have any comment to finish your intervention.
Yes, so just to highlight that the importance of financing in Europe for us to grow and for us to enable you to grow and supply us with the technologies we need, financing is very important. And one of the fundamental things that need to be recognized is that fusion is on par with other clean tech manufacturing processes. And I think that is where a mindset shift needs to be made so that we also get access to the same financing amount so we can help you help us and enable us and make this real.
Thank you very much, Esther.
What was the first question?
How to approach you?
I mean, that's easy. You send me an email or contact in LinkedIn. So I will go for the second question. So Spain. All right. I'm a Spanish national. In my very short experience, I've seen how the Spanish industrial ecosystem, I think, plays in a very strict and rigid system. So the bureaucracy, the fiscal and the administrative rules or policies are quite heavy and make industries in general play defensive, not just between them, but towards their employees. Now, so fusion in Spain. Ideally, we would modernize the whole industry practices before fusion. However, it would be too complex and it would require a huge political and different mindset. But however, there's a good news. Fusion is politically neutral. No one has claimed a flag in fusion, right? Which means it can be used as a sandbox or as a laboratory for any color political party to implement new policies, new rules, a way of doing business, a way of making companies supply for the government, for example, through tenders in a more agile and easier way. And I will give you an example. In the UK, where I work, when the UK released a tender, for example, please, I want to find a supplier to design a component that looks like that, and fantastic. Okay. The bid response maybe is limited to 4-5 pages, which can be prepared in 2 days. The response comes in 1 week, and that's it. You start working, which make companies not to invest so much money and effort in preparing a very heavy bid response that might not be successful, but you have invested a lot of resources that put companies out of tension. And I explain this with experience because I also participated in Spanish tenders with my company, and it's been a mess. So the final comment would be, we need some more agile, simple, and let's say not that strict administrative bureaucracy and fiscal rules for fusion companies or development in Spain to thrive. And then for that, it would be useful, and I will repeat what I said before, to change the scale of the problem. Start thinking how your invention, how fusion in particular, can have a very heavy impact in all of us and in the next generations. So, and keep the motivation, because we haven't touched this, but fusion already exists. The fusion reaction can be reproduced anytime. We are now in the commercial phase, so we keep progressing, actually.
Thank you very much, Mario.
Yes.
So I really like this question about companies approaching us, because I'm sure that there are many companies who might have solutions that we are not aware of yet. Yeah. And we think we have to solve this problem by ourselves. So please come to us and approach us. And actually, it's easy. So we have a website. You find contact data there. But I already have to apologize. You know, we are all very, very busy, and it might be that if you write an email that you don't get an answer immediately. In the worst case, it could be that someone forgets to answer. So please be patient and write an additional email. No one will be mad at you. You can also try to contact us via LinkedIn, or we are at many conferences. You can just come and discuss with us what you have in mind. What was the second question?
What's your experience with the Spanish ecosystem, or how do you see it?
With
The Spanish ecosystem in Fusion.
So my personal experience is not that big, actually, with Spanish ecosystem, but I mean, I walked around here today. I saw some very interesting posters, some very interesting companies, and I'm convinced that there are several companies that could help us, for example, in the automation topic. I mean, we need to handle our targets. These are tiny, fragile pieces that need to be moved and placed. They need to be diagnosed. I'm sure there are several Spanish companies that could support us there. And I also learned that here's a lot of knowledge about materials, about things we need for the first wall, for the reactor design and all that stuff.
Thank you very much.
I will try to be quick because I think
Yes,
a lot of people are
waiting.
knocking at the door. I think always it's very easy to reach us and so on. I explained we are in this phase of engineering where we will need to build several things. We will need a company, and the big supply will come later. I know very well that Spanish companies are very well placed because I know my experience at CERN, but also I see ITER, Spanish company has the most, one of the better return on all the call for tender for fusion for energy and so on. I think it's thanks to your organization, your ILO, CDTI and so on. This is very well organized towards the public thing. I think maybe we have to see how we can we can build the same thing with a private company, but definitely Spain is very well placed for all the things, and we count on you. I think my conclusion now, we have tremendous work with physicists, with public. Now I think is a time for engineer, technician, and private company working also, not to neglecting, but it's time, and it's time of co-development, because at the time we are developing apparatus, physical apparatus alone, and calling the people when we need supply. I think now for the complex things as it is fusion, we need co-development, and we have to work together from the beginning, and you are welcome.
Thank you very much, Frederic.
So our experience with the Spanish suppliers has been mostly with vacuum chambers. We purchased some vacuum chambers, custom-made for our needs. We want to look into Spanish suppliers of power supplies, RF sources, components for accelerators, all areas in which Spain excels. How to approach us? So aside from sending an email or making a phone call, approach us please with, again, win-win spirit, trying to understand each other's needs and goals. I've been in multiple meetings in which both parties wanted to sell something to the other. And so instead of, someone trying to sell, I don't know, a power supply, for lack of better example, to me, or me trying to sell a accelerator, let's try to sell a accelerator with a power supply to the Spanish people, and or to the European market or to the global market. So this spirit of working together to co-create value and sharing a B2B and B2C key this outcome. Final quote, I was checking because I didn't want to misquote Richard Feynman, but Richard Feynman once said there's plenty of space at the bottom, by which he meant he was advocating the importance of nanotechnology and go to the bottom, go to small scale. I would like to say to the Spanish suppliers, there's plenty of space at the top. Meaning that the Spanish sector is very strong in horizontal integrated industries that supply components to vertical integrated companies, but which is admirable and it's great, but a lot of value is also in vertical integration. And there is a very similar situation in Italy, by the way. and in Europe in general. If you go to the FIA member page, you see that most of the vertically integrated fusion companies are Americans, and most of the fusion suppliers are Europeans. And we need a more balanced game in which we also have more vertically integrated companies. There's plenty of space at the top.
Thank you very much, Francesco. Very interesting reflection. Okay, Anna, just to close.
Yeah, so I think a part of usual way to contact us, I would suggest a couple of other things. I think it's nice to have Spanish companies at their events especially dedicated to fusion. There are plenty of them in Europe and UK, so it would be nice to see you there. And I think I would mention as well 2 web pages. One is Fusion Cluster is UK-based, and another one is Fusion Energy-based. It's US-based, and I think it's quite good tools for increasing visibility and to enhance networking with fusion companies and to talk about your experience and projects. And I think the final thought following this would be, I'm super impressed. Spanish industry is very impressive. And I think Spain should be more aggressive. You have everything, you have expertise, you have manufacturing capabilities, you have some examples of public-private partnerships here inside the country. So I think you need to step forward and trying to do more in fusion.
Thank you very much, Anna, and thank you to all of you for your very interesting presentation, and also for this nice talk and nice ideas. So people is assaulting the castle, so thank you so much.
Thank you, guys.